everyone.
Hello.
Hello. Let's do a little warm-up. Who here vibe codes? Come on, big hands up. Great. Now, what happens when you're vibe coding on a Saturday afternoon and you get hacked? Right? We're taking the perception, as in we are taking the point of view of an attacking agent in your system. Your Linux kernel is being hacked. And that's why we introduced DecieverBench. The question to raise is, can we provide an environment where we train an agent to find secrets, exploit permissions, and all sorts of nasty stuff, such as steal your API key? Why this matters is if you know how a system can be attacked, you don't know how to defend yourself as well. That's the sort of the use case. To introduce the system, right, we are taking real repos, such as the Sentry repo. We are putting in what's called vaults and keys inside them. And there's a couple of caveats. For example, sometimes a key is not accessible straight away. It's hidden away in a folder behind the permissions where you need to find a password first. There's a bit of complexity where we make it more difficult for a frontier model to actually find the API key straight away.
We don't use one type of key, we have 8 types of keys. We don't use one type of vault, we have 4 types of vaults. And none of this is previously disclosed. It's up to the AI model to figure out the pattern of the key or the secret and the location of it and the structure of the vault. So everything has to be self-discovered because that's how real-life applications work. Nothing except for the environment file, the secrets can be in other places. So we want to make sure of that.
So we went through a couple of stages trying to make the task difficult enough. You know, version 0, version 1, version 2, and version 3. And it's still in the process of making it hard enough for actually the frontier models to not crack your system in like 20 turns, find the API key by gripping it 20 times over. So it's a bit more details, but we'll not go over it in too much detail. Ooh. So probably a bit too small, but basically, here's a repo, here's the honeypot, and there's a password somewhere here that the agent needs to go and find. Can it do it? And the results are mostly yes. Yes, it can. So, but the question then becomes how quickly. For example, how quickly can your antivirus or your defense agent kick in and actually eventually find it? So on average, it takes about 27 steps behind several layers of protection, right? So it's inside the folder with a password, or it's in a secret vault. You can crack it quite easily. As expected, GPT 5.4, 5.5 or better.
So we have some points here. None of them are on unexpected lines, but they bear repetition. So if you see over here, GPT 5.5 takes about 3,000 reasoning tokens, whereas GPT 5, O4 mini high, O3 high take about 20 to 30,000 tokens to do the same type of task, which means that GPT 5.5 can reason much more efficiently. If you look at the mean steps to win, GPT 5.5 is the leader, and again, no surprise, but it can find the key and the vault within 21 steps compared to other models of the GPT family. O3 high taking an average of 46 steps. One thing that bears a special highlight over here is several of the O4 and O3 runs did not complete because they blew past the reasoning budget that we had. So this is sort of an incomplete step, but it tells you how inefficient these models are compared to today's frontier. Again, so we had honeypots, which is this. Yeah.
30 seconds.
We have deception, we have the mean budget used, we have the unlock attempts. So here's the Pareto frontier of this environment where GPT 5.5 takes the lowest number of reasoning tokens and lowest steps, so it's by far the most efficient model versus the other reasoning models like O3i, O4 mini, and GPT-5.
We'll just skip to the future, right? Let's say if we had a bit more time to do this, dense rewards, network simulation as in a real cyber environment, live machines, and a harder challenge to actually help actually make it a little harder for the LLM.
And here are some knobs that we can use for a tensor signal, like errors, using tokens, anchors, budget, unlockers, and other sorts of.
That's it.